Hello and welcome to the third video in our discussion series about acids and bases. For this video, we will be talking about the strong and weak acids as well as the acid dissociation constant. So acids as well as bases are classified by their strength and the amount of hydronium and hydroxide ions produced per mole of substance dissolved. In other words, by the extent of their dissociation into ions. Because acids and bases are electrolytes, their strength correlates with their electrolyte strength. Strong electrolytes dissociate completely and weak electrolytes dissociate slightly. Now, a strong acid dissociates completely into ions in water. So in this general formula, again, Ha depicts the acid. So as you can see here, we have here Ha or the acids and water, and after the reaction, the strong acid completely dissociates into ions in water. Now, a dilute solution of a strong acid contains no Ha molecules. You only have here the hydronium ions. While a weak acid dissociates slightly to form ions in water. So in a dilute solution of a weak acid, most Ha molecules are undissociated. So recall that K sub C is equal to the concentration of hydronium ions and concentration of the base over the concentration of the reactants, which has a very small value. So as you can see here, there are no Ha molecules in the solution after the reaction if there is a strong acid, while in the weak acid, Ha are not completely dissociated. So for the acid dissociation constant K sub A, we write a specific equilibrium constant for acid dissociation that only includes species whose concentration change to any significant extent. So for the dissociation of a general weak acid Ha, like any equilibrium constant, K sub A is a number whose magnitude is temperature dependent and tells us how far to the right the reaction has proceeded to reach equilibrium. Thus, the stronger the acid, the higher the hydronium ion concentration is at equilibrium and the larger the value of K sub A. So we have discussed last time that K sub A is equal to the concentration of the products over the concentration of the reactants. So always remember that the value of K sub A is an indication of acid strength. Again, the stronger the acid, the higher the hydronium ion concentration, the larger the K sub A. While the weaker the acid, there is a lower percent dissociation of H sub A, also a smaller K sub A. Now, for the ion product constant for water, a change in hydronium ion concentration causes an inverse change in the hydroxide ion concentration and vice versa. So if there is a higher hydronium ion concentration, we should expect a lower hydroxide ion concentration. And when there is a higher hydroxide ion concentration, we can also expect a lower hydronium ion concentration. So there is an inverse relationship between the hydronium ion concentration and the hydroxide ion concentration. So from these two values, we can define the terms acidic and basic in terms of the relative concentration of hydronium ion and hydroxide ions. In an acidic solution, the hydronium ion concentration is greater than the hydroxide ion concentration, while in a basic solution, the hydronium ion concentration is less than the hydroxide ion concentration. And lastly, in a neutral solution, the hydronium ion concentration is equal to the hydroxide ion concentration. So to calculate the hydroxide ion concentration when hydronium ion is known, so we have to remember this formula. The ion product constant for water is equal to hydronium ion concentration over the multiplied to the hydroxide ion concentration. If the hydronium ion concentration is known, we can get the hydroxide ion concentration by dividing the K sub W or the ion product constant for water, which is 1.0 times 10 raised to negative 14 over the hydronium ion concentration. Whereas, to calculate the hydronium ion concentration when hydroxide ion concentration is known, we will divide the ion product constant for water by the concentration of the hydroxide ion. So, always remember this formula. So, this is the relationship, or this is just to show you the relationship between the hydronium ion concentration and the hydroxide ion concentration. For example, a research chemist adds a measured amount of hydrogen chloride gas to pure water at 25 degrees Celsius and obtain a solution with hydronium ion concentration of 3.0 times 10 raised to negative 4 molar. Now, calculate the concentration of hydroxide ion, and is the solution neutral, acidic, or basic? So, we can use the known value of K sub W, or the ion product constant of water at 25 degrees Celsius, which is 1.0 times 10 raised to negative 14, and the given hydronium ion concentration to solve for the hydroxide ion concentration. We can then compare the hydronium ion concentration with the hydroxide ion concentration to determine whether the solution is acidic, basic, or neutral. So, our solution would be to divide K sub W, or 1.0 times 10 raised to negative 14 by 3.0 times 10 raised to negative 4. So, we will arrive at the answer, 3.3 times 10 raised to negative 11 molar. So, based from our answer, the hydronium ion concentration, which is 3.0 times 10 raised to negative 4, is larger than the hydroxide ion concentration, which is 3.3 times 10 raised to negative 11 molar. So, in that case, if the hydronium ion concentration is greater than the hydroxide ion concentration, the solution is considered acidic. So, that ends our third video in our discussion series. Thank you for listening.